In this module, I want to review the concept of radians. And so the fundamental question we start with is, how do we quantify the degree to which the intersection of two lines are separated? And so we call this an angle, and we want to be able to compare quantitatively the degree of separation between those two lines to those two lines to, say, those two lines. And so how can we compare quantitatively what those separations are? And so one way to do this is we start with the two lines not separated at all, and we ascribe that as 0. And then, if we bring it all the way around to the other side so that they're overlapped again, we ascribe that to another number. We could call that 1, or 100, or 360. Then, every other angle is then some fraction of the complete amount, and then that angle would then represent the fraction of the total, whether it be 1 or 100 or 360. And now, of course, 360 is one of the most common, and that's in that we call that degrees. And so in that case, the complete is 360. If it's flat, it's 180. The choice for 360 comes originally from the ancient Babylonians, and the number is chosen because it has so many divisors, and you can divide it by so many integers to get other integers. And so, as fond as we might be of the ancient Babylonians, our computational abilities are more powerful now than they were then, and so this may not be the best choice to determine how to distinguish our different angles. And so let's look at it from a different way. The concept of radians starts with the fundamental definition or the characteristic of a circle, which is for a complete circle, the ratio of the circumference to the radius is the number 2 pi. And so we're going to use that to come up with a more meaningful degree of angle. And so, for example, if I had a radius here, I got two circles. This has a radius of 3. This one has a radius of 2. And if I went very carefully and I measured the distance going all the way around that circle, this circumference would be, say, 18.8496, and this circumference would be 12.5664. I'm going to do this kind of pedantically, but I think it will eliminate any mystery of the concept of where radians comes from. So now imagine I have two lines, and I want to be able to quantify the angle between them. So what I do is I imagine a circle, then centered. See if I can draw that. We have to imagine that that's centered. I didn't get it quite centered. But imagine a circle then centered where those two lines intersect. And now we can look at what's called the arc length. And the arc length is the amount of that circle subtended by these two lines. And what I mean by subtended is what I just described here, the amount of the circle that's contained within those two lines. And I represent the length of that line, called the arc length, by s. Now, you can ask the question, well, how long, what length is that length s? And at the moment, I might not know. But if this is at a radius r, let's say let's do this example. This is a radius of 3 meters. I can draw another circle here with a radius 2 meters. This circle's not very good. And it subtends amount of arc length equal to this length. And the important fact is that the ratio of the arc length subtended by the angle divided by the radius of any given circle is also a constant. Just like this is a constant. And so if this angle here subtends, let's say, for example, if these two lines subtend 1/8 of the circle, then S will be equal to 1/8 of the circumference. So for the radius equal to 3, then the arc length would be equal to 2.35619. I'm giving myself some ridiculous number of significant figures. For r is equal to 2, then the arc length, I have a very good measuring device for that. The arc length for radius equals 2 is 1.5708. And that is assuming that this subtends 1/8 of the circle. Then if I calculate for both of these results, S over R, for r is equal to 3 is equal to 0.7854. If I calculate S over R for this, I get exactly the same result. So just like for any circle, I have this result. For any circle, the arc length subtended by two lines over the radius, this is for any circle, is equal to some fundamental, it's not fundamental, but for a constant. So the radius of the circle doesn't matter. This provides now a way then to define the degree to which the angle then for these two lines. And the way to define the angle for those two lines is this constant. So I can now define the angle between any two lines to be the arc length subtended by any circle divided by the radius of that circle. And that now becomes my definition of the angle. And what happens then, I say, okay, well, what about if the lines overlap each other? If they overlap, then of course the amount of arc length subtended is 0, so that's 0. And then if you go sort of all the way around, then the arc length subtended by the complete, the arc length subtended is the complete circle. So one cycle around then gives you the complete circle, which is 2 pi. So defining your angle this way gives you then essentially a definition of 2 pi for one complete revolution. But it's more useful than that because it gives you a relationship between the angle and the arc length subtended by those two lines. So in some cases, you're looking for what the arc length is for a particular angle, and you can find that by using this relationship. Only in radians. And so it's often necessary to convert back and forth between radians and degrees, and that's easy enough to do because 360 degrees is the same as 2 radians. So if I have 360 degrees, that gives me 2 pi radians. 180 degrees is pi. And so if I have something in, say, 50 degrees, I can multiply that by 2 pi over 360 degrees, and I can get the answer then in radians. The one other important point, we give these angles names, whether it's degrees or radians, and then we convert, a lot like we convert for units. But it's important to note that these are dimensionless. Neither radians nor degrees have dimension. They are dimensionless quantities. Converting between them is just a matter of defining what a full how much is in a full circle. But neither of these have dimension. And so that becomes important in doing dimensionless analysis.